Testing 1, 2, 3. Testing 1, 2, 3.
Welcome to NASA Edge.
An inside and outside look?
At all things NASA, and in honor of the upcoming LCRD, Laser Communication Relay Demonstration Mission launch.
Hey, Blair, we can't hear you.
Deployed my own laser
Blair,
communication
we can't hear you.
system. Yeah, you got to use the earbuds. You got to.
You gotta be part of the game here. I've developed this system, and you guys will not only have audio, you'll have video.
You'll have lots of terabytes.
Lots of data.
Hey, we still can't hear you.
Try harder. Like, listen.
This is not working.
It's nothing.
Everything says you're good. You should be good.
You need to workshop your thing.
What'd you say?
But no, we should be good. Just
Hey,
go
tell
with
you
the
what, here's
show.
what
Keep it
we're
rolling.
gonna do. We're gonna go ahead and continue the show from here. You just work on whatever you're doing, and we'll get back to you. All right, bye. Hey, tell you what, on today's show, we're going to be talking about the Laser Communication Relay Demonstration Mission.
Or LCRD. And we have subject matter experts from NASA headquarters, the
Yes.
Goddard Space Flight Center,
right.
MIT. They're all going to come and talk to us about the evolution of space communication, and in particular, on this show, laser communication.
Well, before we get into the components of LCRD, let's focus on space communication first.
Using my system.
My system.
Jason, can you tell us a little bit about your role with space communication and navigation?
Sure. At SCAN, our job is to enable NASA missions. We enable exploration, we enable science by providing the mechanism by which you communicate to and get data from satellites, whether they're crewed or robotic. And we're responsible for making sure that they can navigate as well. Essentially, we move bits for the missions and we help them understand and know where they're at, how fast they're going, and what time it is. All very important pieces of information.
How will LCRD help NASA missions moving forward?
So LCRD will be our foray into relay in optical from geostationary orbit. Just like terrestrial bandwidth needs, everybody wants to have more bandwidth. We need more bandwidth to accomplish our mission. The thing that we will be learning from that is how to operate an optical relay from GEO. That will help with terrestrial optical needs, but that will also be a learning experience for us about what we would want to do in terms of high bandwidth data aggregation at the moon as we focus on sort of building up that exploration capability for sustainable lunar presence. One of the things that is a fundamental responsibility for SCAN is to enable exploration and science, and lessons learned from LCRD will help us do that in the context of essentially building an internet in space where the sustainable lunar presence will be the framework that will learn all those lessons. Because you want to try and reduce the burden on users, that they don't have to carry as much equipment, right? So you wouldn't want to carry a cell base station around all the time with you with your cell phone. You just want to carry your cell phone. So we want to make sure that the user burden at Lunar is low. We can aggregate that data and send it back over these high bandwidth data links. But then that extends exactly in a replicatable way to what we expect we will need for exploration at Mars. This is exactly the kind of thing that we need to have because the data rate for the things we will learn at Mars will demand high bandwidth. And we expect that the optical will serve that purpose for us.
Will this cut down on the transmission time of the data that we receive?
Unfortunately, we are subject to physics of light time. So we can't hurry it up, but we can get back more.
Jason Mitchell was exactly right. Bandwidth is key.
But before we get any further, I just want to know, you guys,
Are you hearing everything? Are you getting
the data through the laser communication system?
I've developed here? Everything on my end says go. We're good.
Are you talking about this contraption that's in front of us?
Be careful how you mess with that. It's very sensitive equipment.
But yes, and it's working. Everything on my
My end says it's working. I think we're getting good data. And what I want to do for you guys is give you a demonstration and show you how much bandwidth I can actually send you via laser.
Tell them what we had to do.
Well, first we had to tinker with what you gave us to get it working. So now we can actually hear you, but whether or not we are going to receive gigabytes of data from
get
you
ready.
remains to be seen.
You'll receive more data than you've watched on Netflix in the last 6 months.
No, before we get started, you're saying you're going to send gigabits of data through this contraption to Lasercom.
Right now. Get ready. I'm sending it. I'm highlighting. I'm sending it. This is it. Big time. And get ready for viewing. Did you receive it?
Nothing.
Not a
Did you?
thing.
Did you receive? It's there.
All right, Blair, we can't see anything right now, so while your data is in transit, we're going to carry on with the show.
You know, a big part of LCRD is the partnerships involved. And Jade Wang works at the Lincoln Labs at MIT, and she has a big part in this mission.
Yes.
Let's see what she has to say.
Okay.
Jade, I understand you work quite a bit with laser communication or optical communication. Can you tell us, what is laser communication?
Laser communication is using light to transfer information instead of using electrons. So in your computer, usually what happens is you use electrons to transfer bits, like ones and zeros. But with laser communications, we turn those ones and zeros from electronics to light. And so, for instance, you can transmit the same information by like turning on and off a laser pointer.
So how does that work in space? Because obviously we have a lot of infrastructure here on Earth for laser communication, but how do we do that from, say, the LCRD relay mission?
The difference is on the ground, it's being transmitted through these very small fibers. They're like small strands of glass, basically. And in space, what we do is we just beam the light out through free space using a telescope. So kind of like how you can use a telescope to like look at the moon, or if you want to look at where LCRD is, you can look at where LCRD is using a telescope. That's how you collect the light. You can also use a laser pointer and a telescope to transmit light in the same way. And so they'll just propagate over space and through the atmosphere and carry information in exactly the same way.
Now, that's obviously very impressive, but it seems like there's a big challenge when you think of sending information that way, because it's very direct as opposed to radio signals that are kind of broad.
Yeah, that's correct. With radio frequency, the wavelength or the frequency of radio communications is very low, so it's broad. So it kind of goes all over the place. With light, it's very directed, so you have to really point very precisely. Sort of, you know, if you're using a laser pointer and you're trying to hold it on one spot and your hand's kind of shaking and moves around a little bit, we have to point a lot more accurately than that.
Is that going to be as sort of an added challenge for laser communication from space? Because I imagine over great distances, even those subtle shifts in movement are more exaggerated, if you will.
Yeah, that's correct. It is. And what we do is we use an active tracking mechanism. So from the ground side, there's usually a broad beam that illuminates the space side. And the space side uses that beam to figure out where it is. And there's an active tracking such that they can stay aligned to each other.
What's the big advantage? Because I've heard through the grapevine and through my own research that it means I'll be able to download higher quality movies in the future. Is that really the main benefit for laser communication, that volume of data?
Yes, definitely. It's the volume of data. So with laser communications, you can transmit a lot more data. That's because it's at the higher frequencies, and so you have a lot more bandwidth. This is the reason why terrestrially we've replaced a lot of the long-haul copper with fiber optics with laser communications. It's the same exact reason. There's other advantages too, though, because it's so directed, it means we can put the energy exactly where we need it to go. And so that means the satellites, the apertures, the telescopes can be a lot smaller. And so when you're launching something like LCRD to GEO, it costs a lot to get something big, where if you can put it in a smaller package, it'll be a lot cheaper. So that's another big advantage. There's actually a third advantage, which is the RF spectrum is very contested, so you have to buy spectrum in order to transmit over the air. And optical communications, because it's so directed, you're not really like fighting with the other signals in the air. And so you don't have to worry about that. You can just go where you need to go.
That also means that weather might be a factor for laser communication, because obviously you're not competing for space, but you might have to compete with the elements.
You do, definitely. We are sensitive with laser communications to clouds, so when you're clouded out, you might not be able to get your signal. It also means that just going through clear sky atmospherics, we have to deal with what's known as atmospheric turbulence. The signal is going to increase or decrease in power, and it's going to do so over some time period, and you can't predict when you're going to get something loud or when you're going to get something quiet. And so you have to use coding or other techniques to still be able to transfer your data error-free instead of just losing bits and pieces of it as you try to go.
I imagine that's a pretty difficult and challenging thing to do, especially from space.
I certainly am impressed by the people who've come up with all the different codes and the techniques that allow us to do all this.
Now, do you have your own personal ground station where you can have them send data directly to your office there at MIT, or do you have to actually go to the official ground station?
I wish. We have been discussing and thinking about how to make low-cost optical ground station terminals, but I think we're a little far from having one that I can carry in my pocket.
Well, if you figure that out, let me know. I'd like to get in on the ground floor on that kind of opportunity.
So to speak.
Yeah. I like the way you guys think up there at MIT. That's awesome.
Thank you.
You can tell that Jade is having a fun time at Lincoln Labs working on the LCRD mission.
Absolutely. And the partnerships that, are always there with NASA missions, and in this case, between Lincoln Labs and Goddard, NASA has partnerships domestically, internationally, and those type of partnerships are showing up in bright colors here with LCRD.
What's even more important is that during that interview with Jade, we still haven't received the videos from Blair on his laser relay system.
Not one.
Now, see, guys, I'm a little disappointed because we're on a brilliant trajectory there, and then you had to bring this up. Now, I did some research. You have received everything. In fact, Franklin, your disk is full. So it's there. We're going to unpack that. But more importantly, not only was Jade a huge inspiration, but also it's not just about that technology. It's about the mission end to end. It's about ground stations. It's about going from space to the relay, down to the Earth and back. It's the whole picture. And to really understand this, we need to talk to Risha George. She's really involved in the ground station and the aspects of the mission that support just that, the successful completion of LCRD. Not only that, I'm sure when she looks at my schematics, she'll see that just like the ground stations, you guys have received the data you need. Let's hear from her first. Risha, I know you do a lot of work with ground stations at NASA Goddard. How does that relate with the laser communications relay demonstration?
I work on the Access project, which is it stands for, as we have many acronyms at NASA, and this is another one, Advanced Communications Capabilities for Exploration and Science Systems. And we're actually taking over operations of the LCRD after payload commissioning, approximately 2 months post-launch. And we are also responsible for one of the optical ground stations that's located in Hawaii as well. So we partnered with MIT Lincoln Laboratory to install an optical ground station there, which is one of 2 that will provide laser communication services for LCRD.
So once LCRD is commissioned and operational, tell me a little bit about the relay itself. Where's the signal going and how is this going to be demonstrated effectively?
So LCRD will be in a 2-year experiment phase, and there's certain objectives that they want to achieve during this time. We want to understand the optical link performance between LCRD and a user terminal. So there's a space-to-space optical link there to verify and validate and understand how well that works and improve performance where we can. Additionally, we want to understand with the relay function, there will be 2 optical ground stations. So depending on weather and whether there's a cloud coverage or not, and basically establishing line of sight, we'll have an opportunity to relay that signal to one of the 2 optical ground stations. Just in case, there's challenges with weather, there's also an RF radio frequency backup option as well to get data down to the ground. And so what we're demonstrating is the ability to understand those optical links, but also we're testing out extremely high data rates, 1.2 gigabits per second, which is one of the highest data rates that we'll be operating at today.
And so tell me a little bit about this space-to-space connection. You said a user terminal in space. Who's going to be communicating with LCRD?
So one of the opportunities and the users during the experiment phase will be the International Space Station. The International Space Station, there's a user terminal that another organization at Goddard is providing. It's called Illumity, and that will be integrated to the ISS, and that will be one of the first experiment opportunities that LCRD will be able to utilize and demonstrate. And it also provides a great capability for the space station today because for their science data throughput, right now they operate at 600 megabits per second, and so this will give them a much higher data rate.
We also shoot a lot of video up there on the ISS. You could test that throughput by sending some maybe 4K video down at high data rates. Would that be possible if this is successful?
Absolutely. It just takes a connection, between the Illumity space terminal and the ISS as well, which is currently in work. And we're actually going to demonstrate that type of capability on, the Artemis 2 mission. And one of the opportunities there is to transfer high definition video as well as file transfers, which we would not be able to do without having this capability.
I don't know about you guys, but I'm really excited to see the whole picture. And Risha did a great job of talking about this mission end to end, from the ISS all the way down to the ground and how the system's going to be tested. But I got to tell you, I'm a little kind of disappointed. Everything on my end says you've got the data I sent, and I just don't feel like you have the confidence in my system that I think it deserves. So I wanted to kind of walk you guys back to the beginning and talk about some fundamentals. Kind of how laser communication actually works. Like if you think about lasers, they're light, right? It's light. When you blend those two things together and you kind of confuse that, then now I see I've got your attention. So.
While he's talking about that, I'm gonna tell our viewing audience about how NASA Edge traveled to Northern Virginia, to Northrop Grumman to talk to NASA's Javier Ocasio-Perez about the final preps of LCRD in the clean room before it was shipped down to Florida.
And that's how this works. Javier, it is so great to be in the clean room here at Northrop Grumman with the spacecraft that is carrying the payload for LCRD. Can you give us an update on the mission?
Yes, so LCRD is currently attached to the STP-SAT-6 spacecraft. So a little bit of history. LCRD was put together back at NASA Goddard Space Flight Center, where we attached all of its pieces, the flight panel, the optical modules, the flight modems, and other software-related components. Over there at Goddard, it went through environmental testing, including thermal vacuum test, vibrations, acoustics, and all sorts of electrical and functional tests before it got delivered here to Northrop Grumman to be integrated to the spacecraft.
But of course, it doesn't end there. Now that it's here, you had to do even more work once you're here with the spacecraft.
Yes, that's correct. That was just a milestone, delivering the payload here to Northrop Grumman. Then we started a brand new, exciting chapter. We had to do standalone testing with our team to make sure LCRD survived the shipment from NASA Goddard to here. Then we got to the point where we're electrically integrated and then mechanically integrated, and then we became part of the full STP-SAT-6 spacecraft. Then we went through a range of space vehicle level environmental tests, including electrical magnetic resonance signaling, radio frequency compatibility tests, and additional thermal vacuum testing at the spacecraft level.
So Javier, what else is included on STP-SAT-6?
Great question. So LCRD is a hosted payload as part of the full STP-SAT-6 mission. As you can see in the overall spacecraft, at the very top, there's a box called the payload module, which includes payloads and instruments from other locations like the Air Force, universities. Then in the middle, you see the big plate or flight plate, which has LCRD. So LCRD is the biggest payload in STP-SAT-6. And then the rest of the components, the cylindrical shape and the boxes in the bottom are part of the spacecraft of the observatory.
And so tell me a little bit about some of the challenges you've faced during this process.
Yes, so putting together LCRD for flight, it's been a challenging process. So keep in mind that we're demonstrating a technology that was developed by MIT Lincoln Labs. So they developed the technology, but it was not meant to be flown into space. So that's where LCRD came in, and we adapted the technology to fly it into space and make sure that it survives all the space environments. Some of the challenges, we had many, but I'll mention a security aspect. We had some boxes with data that's sensitive, so we had to convert a clean room back in NASA Goddard to be secure, and that involved shutting down access to windows, secure doors, and it took a lot of effort, but it was necessary for the type of work we were doing. Other challenges that we had is sometimes boxes have design flaws, and then you have to remove them from the payload. We had a particular situation with the optical modems back in 2019, so we had to remove them, repair them, and they have to go through a range of environmental tests again after reintegration. And then another one that's very recent is the whole COVID-19 pandemic. It hit us pretty much at the point after we were already delivered to the spacecraft vendor here in Northrop Grumman. So we had to adapt very quickly. We had to use masks, keep the distance. We had to modify how we did the control room operations. We had to keep desks empty in between just to protect our people, because obviously the people are the most important asset for putting together, LCRD and all the hardware.
And of course, you're going to be down at the launch, right? You still have work to do once you get down to Florida.
Yes, that's correct. So right now, we're still here at the spacecraft facility. We are in the phase of doing closeouts, which is basically making sure the spacecraft is ready for launch. We're removing pieces that don't need to be there for flight. We're putting finalization touches on the thermal blanketing to make sure the spacecraft's going to survive the environment in space. After that, we're going to pack and ship, get to the launch site, and then we're going to do additional testing to make sure that not just LCRD, but the entire spacecraft survived the trip from Virginia to Florida. And then at that point, we're going to get ready, we're going to get buttoned up, and then start counting for launch.
Well, keep up the good work, Javier. We look for very good things from LCRD and future tech demonstration missions in the future.
All right, thank you.
You know, guys, it's really cool to see Javier in the clean room, knowing that the spacecraft is healthy. It's down at the Cape now, getting ready for final preps for launch, and looking forward to just a great mission, a great launch, and seeing this technology demonstration actually work.
Yeah, it's going to be special. Javier was a real cool guy, and I was with Blair along for that trip, and he is genuinely excited about what the future holds for LCRD.
And this built on previous missions, like LCD, which was a lunar laser communication demonstration, which was on LADI, I believe, years ago.
That's right.
But now this is sort of the next step.
Big steps.
Yes, that's right.
Yeah, and we want to remind people, be sure to tune in to launch coverage. Be sure to check the website. Make sure that you pay attention to this incredible historic launch. It's going to be a good time. And a lot of people are going to be really surprised and just overflowing with joy and excitement over this mission. And part of that enthusiasm, at least a little bit, they're going to have is about what I'm about to share with you guys. Now, listen, I got to be honest with you. You guys haven't exactly fallen in love with and embraced my own tech demo. I appreciate that. But I'm just going to show you real quickly that I was right the whole time and that my system worked flawlessly, and you guys are going to have to eat crow. All right? So just real simply, I know you don't believe me, but just minimize the call, Franklin, and you guys will see that all along my system worked absolutely flawlessly.
Did you get it?
Whoa.
Terabits.
Read it and weep, guys.
Am I right?
Get out of here.
Genius.
This is not true.
Absolute genius. I am a genius. Thank you, Mike Weiss. Thank you, Jade Wang. Thanks to all the people that made it possible for me to utilize my brain cells in a way that would help NASA and would actually demonstrate this great technology. I just want to thank everyone. And what else can I say? You're watching NASA Edge.
He did something. Yeah. This is something is wrong with this. Terrible.
Gigabytes, terabytes, zettabytes.
I'm a genius.